All right, getting a couple keys for you guys. Getting ready for assessment one. So this was the Pendulum Lab. So Pendulum Lab had to watch this video first to be able to answer these questions. So determining the period of something, that is the time per cycle or wave, whatever it is. So it's the time versus the number of cycles. So in the second one, where you had to figure out the period of a pendulum that makes 10 complete swings in 15 seconds, the period, T is the symbol for that, is going to be time, 15 seconds, divided by 10 swings. So 10 divided by, or 15 divided by 10 is 1.5 seconds per swing, or a cycle of what it is. So doing that. So some of you did that backwards, and so you got to just make sure you're prepared to do that correctly on the assessment. What kind of motion? So this is periodic motion. What force causes it to swing? So that's the force of gravity, or gravitational force is swinging it. And then why does it swing on an arc? So now by the end of the unit, this should be an easier thing to look back on, and this is the tension in the string. So at the time that was new, but now you're thinking about, why does this not go in a straight line or fall straight down? It's because of the tension in the string. And then here you just made a couple of hypotheses about what would happen, and then that's what we tested in the lab. And then here, kind of reviewing some stuff and some things that I wanted you to try to understand. Where's the pendulum moving the fastest? So that's at position 3. Where's it moving the slowest? So this would be position 1 and 5. And kinetic energy is the greatest, is where it's fastest. So a little review of this stuff. Potential energy is going to be the greatest at 1 and 5 at the ends. Momentum, which depends on velocity, is going to be at 0.3. And then acceleration is the greatest. So here, this is something I was looking at how you might hypothesize this. And we look at it in the PostLab question. So the correct answers for that are 1 and 5 for acceleration and net force. So here you did the experiment. You got data. So I put a little bit here. I just put light, heavy, and medium for the mass for part 1. Couple trials, average time for 5 swings. What you should have got then, the period here, if this was 5 swings, I would take the time divided by the number of swings. So 10.5 divided by 5, which is 2.1 seconds. And what you should have found is that roughly these were the same. So the mass should not have affected the period, which is counter to what a lot of people think. They thought the heavier one would swing faster, or some people thought the heavier one would swing slower. And then here, as we changed the length of the pendulum, just went from short, medium to long, whatever it was, here is where the period was the highest. So in that, it took the most amount of time. So let's say if this was 12 seconds, this was 10 seconds, and this was 7 seconds or something. So the short one is going to swing faster, then the longer one is going to go a little bit slower, like that. That has to do with some rotational velocity stuff that we're kind of skipping over. But if you've ever seen a record play, you could think about the speed on the inside versus the speed on the outside. They're going around in the same amount of time, but the one on the inside is moving faster. And when the period is high here, that means it's taking the longest time. So you kind of think of it as high period is slow. There. So you guys did that. That seemed to be okay. Post-lab questions, why a pendulum's a good example of periodic motion. And so simply there is because it repeats over time. So it keeps going back and forth. How could planetary motion be described as periodic? Because the planets go around the sun each year. So a year for us on Earth is different from a year for a different planet, if we're measuring that in going around the sun. So, but that's periodic because we go around once each year. How the velocity of the pendulum changed as it swung. So we talked about this a lot in class, but it speeds up on the way down and slows down on the way up. And then that got us to kind of think about what was going on in terms of force and acceleration. So in terms of force, and you could look back at the notes that we did on this, but at the very bottom, the force of gravity is down, and the tension in the string would be the exact opposite direction, and those would counter each other. So the net force at the bottom of the swing is going to be 0. So those two forces would cancel each other out, and it is, by this point in the year, you know net force causes acceleration. So if the net force is 0, then the acceleration at the bottom of the swing must be 0. So if the net force is 0 at the bottom, where's it going to be the greatest? And so that's at the two ends. So that's at the ends, or you could think about it as like position 1 and 5 from that picture we looked at in the pre-lab questions, or right here at 1 and 5. And so there it has to do with some vector resolution, but the force of gravity is always going to be down. And in this case, the tension would be this direction. And so that would be a smaller vertical resultant of that. If that's something you can process and understand, you remember enough about vectors, there would be a small resultant or component, excuse me, in the vertical direction from the tension vector. Versus at position 2, gravity's down, there would be a bigger vertical component in of the tension vector going this way that would counter the force of gravity, leaving the net force on it to be less. Last couple ones kind of review, but just kind of thinking about some stuff. So theoretically, would it swing from position 1 to position 5 and back? That's a yes, because theoretically, energy is conserved. So there'd be no energy lost. But in real life, right, you know that it's not going to swing that far. So this would be a no, because energy gets lost to the surrounding. So it's not lost in general, but it's lost from the pendulum itself. And that's kind of what the last question I wanted you to think about. So why, in terms of energy, it wouldn't swing back and forth? So friction with the air converts kinetic energy of the pendulum into thermal energy. So heat created from that. So that goes off to the surrounding, meaning the pendulum doesn't have as much energy, doesn't swing as far, and that's why when you make a pendulum and you swing it, it eventually comes to a stop. And that's it.